Chapter 1 covers matter, energy, and the universe. And that's actually a pretty broad topic, and I promise it's not going to be that in-depth. Welcome to Chem I. My name's Ethan Burke. I'll be your instructor for this course. And just a friendly reminder, this course is not for any type of credit at the moment. It is merely for your benefit and gain to become familiar with the material and ready to go for either AP courses, collegiate chemistry courses, or just a review of the basics. So let's dive right in. Anytime there are written notes like this, I'm not going to read every word that's on the page. I leave that to you. We'll fill in blanks as necessary, and I'll have sections of things where you'll be able to circle words that apply. There aren't any in this area. Actually, there are right here. And you'll be able to circle things that apply. So let's dive right in. We're going to go over things that are pure substances, elements, and compounds. I trust that you'll read those things. But then we get two types of mixtures, and we have homogeneous mixtures and heterogeneous mixtures. And homogeneous mixtures are uniform throughout. And both of these can be separated by physical processes, right? So that leaves a heterogeneous mixture to be non-uniform throughout. And these can both be separated by physical processes. So no chemical reaction required. Let's say we have a solution or a suspension of some compound that doesn't dissolve in water. We can filter that off, and the homogeneous mixture can be separated by physical processes. You can do the same thing with a heterogeneous mixture by, let's say, some particles are attracted to a magnet, so you can put a magnet next to it and attract all the particles to one side and then pour off the liquid, so you can do things that way as well. So chemistry basically deals with micro and macro. And we get something... Oh, what did I just click? Crud. Process says. There we go. So we get the atom molecule topic. And atoms are, of course, the smallest units of elements, right? Smallest units of elements. And they contain only one specific type of atom, right? If you need a list of all the elements, I invite you to look at the periodic table. We won't go through that yet, but you'll learn trends on that later in this course. Molecules are a combination of two or more non-metal, and it's either atoms or elements. And the answer here is definitely going to be atoms, right? Two atoms coming together make a molecule, not whole elements. And they're held together in a specific shape by very strong attractive forces, and in chemistry we call these bonds. Okay. Chemical formulas give symbols of the elements and the subscripts, which indicate either the proportions of elements in an ionic compound or the number of each in a molecular compound. Now I'm saying words as to compounds, so we'll make a little chart here. There are two types of compounds. There are ionic and molecular. Ionic is a metal plus one or more nonmetals. Molecular compounds are all nonmetals. So using that, right, we can go to these examples up here. And we don't see any metals until we get to this BAS. So these all are molecular compounds, right? This is ionic, this is ionic, this is ionic. Barium's a metal, sodium's a metal, calcium's a metal. Then we get water, hydrogen peroxide, and glucose, which are, again, molecular compounds. Just to be able to differentiate the difference between those two. We'll now talk about properties of matter. And it's actually convenient to classify things based on the way that these properties behave. And we can describe the properties as four different things, but they're in sets of two. The first distinction is between extensive properties and intensive properties. Intensive properties are independent of the amount present. So intensive properties, right? does not depend on the amount of substance present. Extensive then does, right? And we can attribute these to examples, right? Temperature, right? Temperature is intensive, does not depend. Volume is extensive, it does depend. Mass is extensive, it does depend. Melting point is intensive, it does not depend. Density is intensive, but energy is extensive. And now I'm flying through this, but let's take a moment and just talk about these now that we have them circled, right? Temperature is intensive, and this is why, right? Does it depend, right? I have a pot of coffee or even a cup of coffee, and I've just made coffee in my Keurig coffee maker, and I have a cup of coffee, and it's at 198 degrees Fahrenheit because that's where the Keurig makes the coffee maker, and I pour it into 2 different cups. Do those 2 different cups, at the moment that I pour them and separate them, have the same temperature? Okay, ideally, yes. Ideally, yes. And that is indicating that it doesn't depend on how much coffee I have, but rather the temperature of the particular sample I'm looking at. So it doesn't depend on how much, therefore it's intensive. Volume's a different story. Let's take that same example where I have a cup of coffee from my Keurig. I separate it. I pour it half and half into 2 different cups. Well, each volume is half of what it used to be, so it is extensive. It depends on the amount present to determine the actual value. Mass, of course, is the same way. As you grow up, you tend to weigh more. This is just because you're growing. I'm not calling you fat. Don't worry. As you grow up, right, as you progress from childhood into your teenage years into adulthood, you tend to weigh a little bit more, and that's because you are growing. Your bones are getting bigger, right? Your muscle fibers are getting strong, and your brain's getting bigger because you're learning a lot more, right? So your mass will go up. It depends on how much mass there is to report how much matter there is in a particular space, so it is extensive. Melting point. Now, melting point is something that's actually used very often in organic chemistry. And I've placed it on the notes for you so that you can see that these things can be attributed to all walks of chemistry. Okay? Organic, inorganic, biochem, nuclear chem, stuff like that. The melting point is the species at which a solid substance melts into a liquid. For water, right, melts at 0 degrees Celsius or 32 degrees Fahrenheit. Right? And for example, benzoic acid. Right? Benzoic acid is an organic compound. I'm going to draw it for you. Right? That's what benzoic acid looks like, and it's a terrible drawing. But benzoic acid has its own melting point. And let's say that is just around 122 degrees Celsius. Right, so if I had a solid sample of benzoic acid, it would melt right at 122. Density is intensive, right? Let's say I have that coffee once again, and let's say I made it extra strong, so that coffee was super concentrated. And let's say I added some milk, right? Let's say I added some creamer before I separated it, and then I separated them, right? Would the density of the original coffee be the same as the 2 individual aliquots? Yes, it definitely very much so would. So it is intensive. Right? The energy of something, right, the amount of energy that it has is something we're going to deal with over in Chapter 5. And the energy, believe it or not, turns out is extensive, right? The amount of energy that something contains, right, depends on, right, how much, the amount of energy is directly proportional to how much work is put into it, right? Work and heat. Now, there are 2 other types of properties. Remember, so I said it was 2 sets of 2. There are also physical and chemical classifications. So we're going to go ahead and classify physical or chemical properties. Physical properties can be measured without converting the substance into another substance. So basically, without a chemical change, you can observe it, right? You can observe it or test it without changing things, right? Temperature. Can you measure the temperature of something without chemically changing it? Heck yes, you can. We have thermometers. Color. Can you look at something and tell me what color it is without making it undergo a chemical reaction? Heck yes, you can. If something's combustible, can we just look at something and say, does that burn? Okay, so most of the time, if you try to light something on fire, you can, but we would have to chemically change it, right? So we're converting some sort of fuel, we're adding the oxygen from the air, we're combusting it and producing carbon dioxide and water. So that would be a chemical change, meaning that how combustible something is, I'm making up words now, is a chemical property. A density is a physical property. Hopefully you've done a laboratory experiment where you dissolve some salt in water, and you take the different densities by weighing out 10.00 milliliters and dividing by 10 to get grams per milliliter. You'll see that the more salt you dissolve, the more dense the liquid gets. So density would be an extensive property. I'm just kidding. It'd be intensive. So be careful of talking your way into things like that, right? Remember that the solute to solvent ratio could be extensive, but density in itself is an intensive property. So just a little trick question review for you. Melting point, like we talked about, each species has its own individual melting point. We're going from solid to liquid, but that doesn't mean we're going to a different chemical, so it is physical. And reactivity with acids, and I'm giving you the word reactivity, right? Reactivity, so it's got to be chemical. So we're going to do our states of matter, and we're actually going to do this in a little bit different of a fashion. I'm going to put an arrow to over here, and we're going to draw a picture involving the states of matter. Just quickly going solid, liquid, gas. Solid, right, particles are really close together. They're not moving. They're stationary. Liquids, they're moving around just a little bit, but they're still contained within the volume. Gas, they are bouncing off the walls. Crazy, super awesome, fun, whatever. So we're going to draw ourselves a picture. So we're going to go gas up here, liquid, and solid. I cannot win with the word solid. There we go. Right? And there are changes, phase changes, that go down and up. And you are expected to know these for the quiz. They are very important. Right? Now we're going to label them 1, 2, 3, 4, 5, and 6. And we're going to write them over here. Actually, we're going to just go one by one. So number 1 is going from a solid to a gas, so it doesn't pass through liquid phase. It just turns into a gas right off the solid. If you have dry ice and you leave it out, you'll actually see there's a little bit of it looks like a smoke, but it's really just carbon dioxide coming off. So solid to gas is called sublimation. I will try and keep my handwriting very neat. Okay? Number 2 is going from liquid to gas. Right? This we know as vaporization. Right? It can be called evaporation. That's acceptable. Make a little cleaner arrow for you guys. It can be called evaporation. I choose to call it vaporization. It's just kind of how I roll. Number 3 we see is solid to liquid. Okay, that is known as melting. Think solid water to liquid water. Right. Number 4 is liquid to solid. So if we're thinking ice, we're going water to ice, right? What's that called? Freezing. Number 5, gas to liquid, is known as condensation. And gas to solid is known as deposition. So, leave that there for a few seconds so you can write it down. Feel free to pause the video also if you need more time. So, we have that pretty diagram. That'll come in handy a lot later. So, we have things called SI units, System International. And they have things like the meter, the kilogram, the second, the Kelvin, which is way better than the foot and the inch and the pound, because base 12 systems are horrific to work with. But base 10 systems are super, super easy, so we use base 10. The prefixes that are in bold here are the ones that you need to know and should be able to use without me giving you a conversion table. You should also know the fundamental units for each amount of measurement, right? Noting that mass is the kilogram, that length is the meter, that temperature is the Kelvin. Okay, the Kelvin. Now, the basic main idea of the rest of this video is going to be something called dimensional analysis. Dimensional analysis is merely the means in which we use to convert units from one area to another, right? So we're going to convert 5.26 kilograms to grams, right? Provided for you right here is converting, or conversion factors. So we're going to convert 5.26 kilograms to grams. Now I always like to write everything out, okay? I always like to be as meticulous as possible to make sure I don't leave everything out. You start by writing down what you know. Again, the 5.26 kilograms that I will write in a nicer handwriting. Right? And we need to multiply this by a conversion factor, right, that cancels out kilograms and leaves me with grams, right? So since we're multiplying with fractions, if we multiplied this together, we would have kilograms in the numerator. So I need something that has kilograms in the denominator, but grams in the numerator, so we're left with grams. And it turns out that if we put 1,000 grams down here, we would get kilograms squared over grams. Well, we don't want that. So I guess we can't put grams down there. Wow. Wow. What if we did this? 1,000 grams per 1 kilogram. Well, that works. Kilograms cancel out. Wow. And we are left with 5,260 grams. Right? Also, if you wanted to be super specific, you could go 5.26 times 10 to the third grams. Also fine. So try this next example question by yourself really quick. Pause the video and see if you can do this. So we're going to set this up the exact same way that we set up the previous problem. We're going to write down what we know. We have 1.4 liters. And we have to multiply it by some conversion factor to get to milliliters, right? We want milliliters, so we're going to place milliliters on the top, liters on the bottom. In 1 liter, there are 1,000 milliliters, right? Liters cancel out, and we get 1,400 milliliters, which is also 1.40 times 10 to the 23rd, wow, third milliliters. Now, we're going to do one more type of unit conversion, and this one's a little bit different. We're going from square units to another set of square units. Now, this means you need to multiply by your conversion factor twice. which is why you have this nice little hint, centimeters squared equals centimeters squared. Okay, so say it a little bit differently. Your work is actually going to look like this. So, 459 centimeters squared times, right, 100 centimeters to 1 meter. Now, you could just write squared. That's fine. I get that the exponent only applies to the 1 meter over 100 centimeters. However, I like to write it out both times. To ensure that I am doing all the steps. Now, you don't have to do that if you don't want to, right? I just recommend it because it yields less mistakes, especially on a quiz. So when you do the math, you get 0.0459 meters squared. This works because one of the centimeters cancels out with one of the centimeters. The other centimeter cancels out with the other centimeters. Now we have meters times meters, or meters squared. There are two metric conversions that you should commit to memory. Obviously, I won't really have an idea if you do or not, but this would be wise for you to have under your belt. 2.54 centimeters equaling 1 inch, and 454 grams in a pound, or 2.2 pounds per kilogram, or kg, right? Now, we're going to do an example using more complex units. So we're going to do grams per centimeter cubed. This is actually a form of density. So we're going to go grams to centimeter cubed to pounds per inches cubed. So this is going to be a longer one. Bear with me. Write this down as we go. If you would like to try it by yourself first, feel free to pause the video and try that out. So starting out, we're going to do the exact same thing we've done for the other problems. And we're going to write out our 8.96 grams per centimeter cubed. Now, we're going to choose a unit to convert. Now, I'm just going to go grams to pounds first, because it can go a little bit faster. Right, it's only one step. Right, so 454 grams in 1 pound. So grams cancel. We're left with pounds in the numerator. Cool, that's what we wanted. Now we have to go centimeters cubed to inches cubed. Right, so just like that problem where we had square units, but now instead of doing our conversion factor twice, we have to do our conversion factor 3 times. 3 times. Right? So we want inches in the denominator, right? So we put inches where we want inches, right? And we go 2.54 centimeters. And we do that 2 more times. Right? Take a second, punch those numbers out. Right? And when you get your answer, you're going to get, right? And we're just going to triple check, right? One of the centimeters cancels out with a centimeter. Another of the centimeters cancels out with the centimeters. The last centimeter cancels out with the last centimeter. We have inches, inches, inches. So we have pounds per cubic inch. We're in a good spot, right? And we get 0.323 pounds per cubic inch. Now, really, it's just one more thing that we're going to talk about, We might have a couple more examples, but this is the last big concept, right? Things called significant figures. Now, significant figures have to do with the level of precision that you can report your answer to, okay? All non-zero digits are significant, okay? I'll leave it to you to read all these specifications. It only takes about 2 minutes to get through this, right? You can look at the couple answers here, right? And we will have, definitely there will be questions on your quiz as to whether a number has a certain number of significant figures or if a particular number or place holding 0 is significant. So let's just do a couple of practice questions, right? In 297, none of those digits are 0. All non-zero digits are significant, so there are 3. In 19.0, the 0 is following the decimal place, or it's to the right of the non-zero digits, so there are 3 significant figures. In the next example, there is one non-zero digit, and both zeros are to the left of the non-zero digit, so they are just placeholders. There is 1 significant figure. In the next number, there are 4 significant figures. The 1 to this 0 right here. And in the last number, since there's a decimal point and the 0 is following the other non-zero digits, there are 3 significant figures. It is not ambiguous. Okay. For addition and subtraction, you may report your answer to the lowest number of decimal places that you have. Okay, so to the lowest precision is where you can report. So in this number, we have decimals that go to the hundredths place. In this number, we only get to the tenths place. So we can only report our answer to the tenths place, or 21.5. Right? Oh boy. Right. In the following example, we have thousands place, ones place, and tenths place. So we only really can report our answer to the ones place, and we can only write 17. Rounding rules. So, new rounding rules. In chemistry, somebody decided that we like even numbers. So we want the number to be even if at all possible. Okay. If you have an even number and there are decimal places following that or integers following that are 5,0,0,0,0 or lower, so basically exactly halfway between the even number and the odd number. So like not 0.501, not 0.0005001, no. 0.5000000 is going to infinity, exactly half. You round down to the even number. If you have an odd number and 0.500, or exactly halfway between the odd digit and the even digit, you round up to the even digit. Okay? So, 1.985 would be 1.98. 1.9851 would be 1.99. 1.995 would be 2.00. Right. Notice the difference between 8.5 and 9.5. 9.5 went up, 8.5 went down. Significant figures in multiplication and division work a little bit differently. In multiplication and division, you may report your answer to the lowest number of significant figures you had in your problem. So, in this example, we have 4 significant figures in this number, 3 significant figures in this number. So regardless of the decimal places, right, we can report our answer to 3 significant figures. Right? So we get 1, 2, 3, 14.9. In this example, now we're going to do it 2 ways. We're going to go if 2 is exact and if 2 is not exact. So remember, unit conversions that are exact numbers. For example, 1,000 grams in a kilogram. It's not 1,000 ambiguous grams in a kilogram. It's exactly 1,000 grams in a kilogram. You don't need to count that to or from significant figure values. Okay, it just is. Okay, so let's say that 2 is exact, so we're going to ignore it. We have 5 significant figures and 4 significant figures, so we could report our answer to 4 significant figures. We would be able to say 5.865. I'll write that a little nicer for you guys. If 2 is not exact, we can only report our answer to 1 significant figure, so we would have to say that it was 6. Now let's say we're taking the average of something. We're adding things together and we're dividing, right? Now, spoiler alert, dividing by 3 does not mean I can only report my answer to 1 significant figure. Okay, since it's averaging, that's a little bit different of a story, right? Adding 1.09 plus 0.938 plus 1.04, I can only report, right? Now you can include the 8 in your calculations by all means, but I can only report to the hundredths place. So when I add those up, and I can only report to the hundredths place, right? I have to say it's 1.02. Okay. Reading this nice little underlined thing at the bottom. Very, very important. When doing multiple operations with a single calculation, do not round off to the proper number of significant figures until the end. Okay, this will minimize your rounding error and increase the accuracy in your final result. This is the last the last section. Just going over density really quick, and then we'll be done with chapter 1, and you'll be ready to do some practice problems and take the quiz. So that is coming. Good luck on that, by the way. Right? I'm going to do problem 1. You're going to do problem 2 as a practice problem. We'll talk about precision and accuracy. We'll talk about Kelvin, and we will be done. The density of solid copper is 8.96 grams per cubic centimeter at 25 degrees Celsius. So what is the mass of 4 cubic centimeters? Well, if we do it is exactly the same as we do all our other dimensional analysis, 4.0 cubic centimeters times 8.96 grams per 1 cubic centimeter, right? Cubic centimeters cancel, right? So your answer is merely 4 times 8.96, which is 35.84. But I can only report my answer to 2 significant figures. So I usually like to write a little arrow, put 2 significant figures, make a little jellyfish, and say 36 grams. Go ahead and try number 2 by yourself. We're going to talk, and there's number 2, by the way. If you want to look at it, pause the video, go ahead and do that. Okay. Now, last thing, precision and accuracy. Ready, set, go. Precision. How close values are to one another. I'm actually gonna change this. I'm gonna say how close experimental values are to one another. How close experimental values are to the true value. So we use the classic dartboard exam with precision and accuracy. Forgive my awful dartboard. Right? Let's say there's 3 friends playing darts. The green dots are neither precise nor accurate, right? They're not close together and they're not close to the bullseye. I'm actually not going to say neither. I'm going to say not precise or accurate. The red dots are close to the bullseye, but they're not very close to each other. So we're going to say the red dots are accurate, not precise. And the blue dots are really close to each other, but they're not close to the bullseye, so they're precise, but not accurate. So, last thing you need to know is how to go from Celsius to Kelvin. I don't really care that you can go from Fahrenheit to Celsius or Celsius to Fahrenheit. I will never ask you about Fahrenheit in this class. Celsius to Kelvin equals your degrees Celsius plus 273, which is Kelvin. Technically, it's 273.15. I'm just going to go with 273 is fine for your intents and purposes in this class. So that is chapter 1. Remember to do this as your practice problem. There will be a problem like it on the test. Again, knowing your significant figures would be awesome because on your quiz you will be expected to report your answer to the correct number of significant figures on dimensional analysis questions. These dimensional analysis problems right here would be super, super helpful for you, so make sure you take a look at those again. Your prefixes that you need to know along with your fundamental units, your states of matter along with your properties and classifications would be great to have on hand. And lastly, everything we did to do with mixtures, atoms versus elements, and classifying compounds. So that was chapter 1. I hope that this is coming pretty well to you. Hope that the notes made sense. Best of luck on the quiz, and I will see you in chapter 2.